Hello and welcome to the Introduction to Docker video. My name is Daniel from Melio AI and I'm here to help you with Docker so that you can upload your model to Highwind. If you've never used Docker before, that's okay. We'll be going through everything step by step with a demo for you to follow along with. Now, this is not a comprehensive Docker tutorial, so some theory and concepts have been left out. We'll only be focusing on the most practical concepts. With that being said, let's get started. Essentially, Docker is a tool that puts your application into a self-contained box known as a container. This means that the app itself and any other dependencies needed to run your application will be stored together and ready to go. And the cool part is that as long as the target machine has Docker installed, you can pretty much run your app anywhere. Okay, so why should you care about using Docker? You know that your application runs fine, you've tested it, and everything works as expected. Let's say you have your Hello World app and you want to run it on a friend's machine or deploy it to the cloud, but then you realize that it's not working. What's going on here? The problem is that every machine is different. We have different operating systems, different runtime versions, and different dependencies. So how do we get around this? This is where and how cool containers are. Docker will help you pack your application and its dependencies into a single container. Now all of these containers are standardized, which means that you can deploy your application pretty much anywhere you want, with everything working right out of the box. And this concept applies to Highwind too. We're going to run your containerized model as well as the models submitted by others in the competition. With Docker, you don't need to worry about anything else. Just upload to Highwind and it'll do the rest. Go to the Docker website and download Docker Desktop according to your operating system. For Apple users, make sure to check if your Mac is running an Intel x86 or Apple Silicon ARM system. You need to download the correct version of Docker to work on your system. Before Docker can create a container, it first packs up your application with its dependencies and then forms a read-only file called an image. Docker then reads this image and creates containers from it. Machines will use this image to create their own containers and run them. Remember, images themselves are not containers. Think of the image as a class and a container as an instance of the class. So where do we get images from? The main place to get them is from Docker Hub. Think of it as a GitHub repo that is just for Docker images. Here, you can find official images or images that have been uploaded by users. You can even build your own images, and I'll show you how later on. Before we begin our first Docker command, it's a good idea to get used to writing them in the terminal. Although Docker Desktop provides a useful GUI for you to use, I highly encourage you to use the terminal as chances are you won't have access to Docker Desktop. With that said, let's take a look at our first Docker command. Here we have Docker pull Python. We use Docker to call Docker, and we want Docker to do what? We want Docker to pull, which means to grab or download an image from Docker Hub. And which image? Here, Docker will pull the Python image, which is an image that contains the Python interpreter. So now we'll have an image that can run Python scripts or applications. Now let's look at tags. Basically, tags allow us to give an image a specific version or label. We've seen the Python image on its own, but notice that this time there are tags included after the colon. Let's look at the Python image with the latest tag. By default, when you pull an image and you don't specify the tag, it will always grab the image with the tag of latest. This is the default action. This means that adding the tag latest is optional, but if we add the tag 3.12.2, we specifically download that version of the image. So just a slight caveat, it's easy to mistake any image with the latest tag as the latest and greatest version. For example, say I build a new image and don't tag it. So by default, it gets the latest tag. But later, I build an updated version of the image and tag it as new. Now I have two versions of the image, but we know new is actually the most recent image. So here we are at Docker Hub and we can see all the different types of images that are available. But what I want to do is to look for the Python image. Then we'll see Python in the results and we can see that Python is an official image and usually that means it's safe to use. Okay, so let's take a closer look at this image. Here you can see they've given you the pull command, Docker pull Python, so you can just copy and paste that if you want to. But I want to see the other tags that it has. So there's quite a few tags. If we click on the tags tab, then we can see all the different versions available. But I specifically want to look for 3.12.2. Now there are quite a few other versions of 3.12.2, but don't worry about those. Let's just look for the standard one. Now that we found it, we can see that its tag is 3.12.2. So in the terminal, we're going to run docker pull Python, and this will pull the Python image from Docker Hub for us. Next, I'm going to try pull the Python image with tag 3.12.2. I'm also going to try pull the Python 3.12.2 Slim version. Before we can build an image, we need to create a set of instructions for Docker to follow. These instructions form a Dockerfile. Now to use the Dockerfile, we need to use the docker build command. At the top, we have docker build -t myPython image. For Docker build, we want Docker to build an image. -t, this is to tag the image with a specific name. And in this case, we are going to name the image my Python image. Then tag is used to give the image a version. Again, if we don't tag it, by default, it will get the latest tag. Here, we tag it with test and 1.0.3. The dot means the path location of the Dockerfile. Usually, you run the build command in the same directory as the Dockerfile. So here, we just add a dot to say the Dockerfile is in the current directory. By default, build will look for a file called Dockerfile, and if it is named something else, we need to use the F flag to specify the name of the Dockerfile. In this case, I have a Dockerfile that is named my Dockerfile. Now, let's go through the Dockerfile itself. To build our image, we need to use a base image as a foundation. So far, we have been using the Python image as our base image. There are other images we can use as well, such as the Ubuntu image, the Node image, and even the .NET image. Think of this as installing Python to your computer before you start running any Python scripts. Now, the Python image itself uses Linux as its base image, so this means that we have the Linux user space included with the image. What work directory does is that it creates a new folder in the root directory of the user space. This is the folder where the image will now be working from. Copy is to copy a file from the source to the target. Here, we are copying the requirements file to the work directory. Notice that it is just a dot. That's because here, the current directory of the target is the work directory. Run is for commands to be executed during the build process. Here, we are running pip install using the requirements file we just copied into the image. In the second copy, here we are copying everything inside the folder my code directly into the work directory app. Now, this does not copy the folder itself, just the contents. Notice that the target is now app. This is interchangeable with dot, but writing app is more clear. Expose just serves as metadata to tell users which port this container should listen from, but it doesn't actually publish the port. We'll see how to publish ports later. Command is the command to be run after the container is launched. Here we are going to run the Uvicorn web server. However, sometimes you'll see that entry point is being used instead of command. What's the difference between the two? Well, confusingly, entry point and command can be used to define the main process that will run in the container. But entry point cannot be easily overwritten, whereas command can. A more standard practice is to use entry point to define the main process and then feed it parameters via command. If we look at this example with entry point, we can see that this is very similar to our previous example, but this time we are using entry point and command together. Here, in entry point, we'll start the Uvicorn web server but then use command for the parameters. Here we have Docker image list. This is useful to see all the images you have downloaded or built on your system. Then we can use Docker image remove to remove the images from your system. Here we can see the main.py file. This is just a simple FOSS API endpoint where the greet endpoint returns hello world. And in the requirements file, we can see that we have FOSS API and the Uvicorn web server. And here we have the Dockerfile. This is pretty much the same as the example. The only difference is that I've added a new run command where I install nano. Now notice that the Dockerfile is within the same folder as the FOSS API folder. Let's look at the copy command. As we mentioned before, the dot refers to the work directory app, but I'm going to change it to app so that it's more clear. Now let's run the docker build command. I'm going to tag my image as my FOSS API image, and we put the dot because the Dockerfile is in the current directory. Now that the image has finished building, I'm going to use Docker image list to see my new image. Because we didn't tag our image, it has been given the tag of latest. Now let's build the image again, but this time with tag 0.0.1. Then I list the images again. Then here we can see the same image, but with the tag of 0.0.1. Now I'm going to remove the images. So now that we have our first image, let's start a container. Here, Docker run is used to start a container based on an image, and the image we have specified is my Python image. The D flag means to run the container in the background so you have control of your terminal. P is to publish a port. This will map a port from the host machine to the port on the container. To clarify, here we will forward traffic from port 8080 on the host machine to port 80 on the container. --rm is to get the container to remove itself as soon as it stops. --name is to give the container a name. If you don't name it, Docker will assign the container a random name. You also can't have two containers running with the same name. -it is to start your container in interactive mode, where you connect to the container's terminal, similar to SSH. By default, a container will stop as soon as it has completed its task, and then we can no longer interact with it. Say your container's purpose is to print hello world. After it is done, it will stop. Sometimes we need to test the container, so we don't want it to stop right away. So to prevent it from stopping, we need to give the container something to do. In this case, we'll add tail f devnull, which tells it to search for a file called devnull, which doesn't exist. So it will keep searching forever, and as a result, it can't complete its task, and thus the container will never stop. Here we have some useful commands to help you manage your containers. Docker process is used to show all the containers as well as their details. Docker inspect is used to see the configuration of container. And Docker logs is used to see whatever the container has outputted. This is useful for debugging. Docker exec it my container bash will connect to an already running container's bash shell. Since the previous image has been deleted, I'm going to rebuild the image again. And then I'm going to use the docker run command based on that image. You'll see that the UVcorn web server has started, but I don't have control of my terminal. I can't really do anything with it right now. So I'm going to push Ctrl+C to cancel and shut down the web server. This will stop the container, and then I'll have control of my terminal again. Now I'm just going to expand my windows a bit so we can see more clearly. But if we run Docker process, we can see the container ID, the name of the image that was used, the command, when it was created, and its current status, ports, and names. Here we can see that our container was exited 55 seconds ago. And also remember, because I didn't specify a name for the container, Docker has automatically given this container the name of Nervous Proskuriokova. This time I'm going to run the container again, but with the D flag, so that I'll have control of the terminal and the container will run in the background. But let's go to Docker process to check it out fully. Here we'll see that the container is up and running. It's been up for 4 seconds. And because it is up, it is listing on port 80. Also, notice the new name given, Thirsty Archimedes. Using the new container name, I'm going to stop the container. Instead of the container name, I can also use the container ID. So here, I'm going to use the container ID to start the container. And then to remove a container, you have to stop the container first before it can be removed. Then when I run Docker process, you'll see that Thirsty Archimedes is now gone from the list. So now I'm going to start a container again, but this time I'm going to give it a specific name, and I'm going to call this container Fast API Container. Then we use Docker process and we can see that Fast API Container is up and running. I'm now going to use Docker logs to see if the web server has outputted anything. I'm going to stop and remove the container and then start the container in interactive mode. Now I'm in the container itself and we can see the output from the web server, but again, I can't do anything with it at the moment. So I'm going to push Ctrl+C to close the web server. To see the configuration of the container, we're going to run docker inspect. We can see a whole lot of information, but it's not important for the time being. And lastly, I'm going to go run docker exec it into the container using the bash shell. From there, I'll be able to access the container's user space and access all the files and folders. Then to exit out of the container, simply type exit. Previously, we've seen that when the container is running, it listens on port 80, but we are unable to reach this port because we have not mapped our local host to the container's port. So I'm going to run docker run with port 8080, which is the host port, and map it to port 80 on the container. Now, when we run Docker process, you'll see the ports 000, 8080 mapped to the container's port 80. Now, if we open our browser and go to localhost 8080, we can see it returns hello world. Docker containers are supposed to be disposable. Generally, as soon as a task has been completed, it gets removed to save resources. So any changes that you have made inside your container will disappear once the container has been removed. This can be a problem if you created new files in the container or made adjustments to your code. Remember, the container is an instance of the image, and the image only has the code that you copied into it at the time it was built. So if you want to make any changes to your code, you have to rebuild the image to copy in your edited code. Since we shouldn't store output or changes in our container, we need to use a form of data storage that is separate to the container, and this is where Docker volumes come in. Now, there are several types of volumes that Docker uses, but here we'll only focus on bind mounts. This is where we'll use a file or folder on the host machine and link it with the container. Think of it as plugging in an external hard drive to the container. Data is no longer stored in the container but in the volume, so the data will persist when the container is removed. Once the volume is created and linked, the container will read directly from the volume, so there is no need to constantly rebuild the image. Here, we'll start a container with a bind mount volume. The v flag tells Docker to create a volume. Then we give it a path on the host machine and then a path on the container. Writing the full path can get tedious and error prone, so rather use print working directory pwd, which contains the location of the current directory. Make sure you're running pwd from the correct directory though, or you might mount something else by mistake. Because I'm going to use volumes and use the bind mount volume, I'm going to make some changes to my Dockerfile. First, I'm going to comment out copying my code into the work directory. Since I'm mounting the folder itself, the folder my code will be available. But because now the main.py file is inside my code, I need to change the command a little bit to let UVCon know that the main.py file is now in my code instead of the root folder. Now that the changes have been made, I'm going to rebuild the image. Next, we're going to use docker run, but we're also going to use the v flag to bind the present working directory to the work directory in the container. Now that the container is running, I'm going to use docker exec to go into the container itself. Now I've opened main.py in VS Code, and I'm also going to cat the code from the container. They should be exactly the same. Okay, great, both of them say hello world. Now I'm going to make changes to the code in the container. You'll see that as soon as I save, the changes are immediate. You can see that in both the container and VS Code, they both have this is new. This is because they're using the fast API folder as a volume. Now I can also make changes from VS Code and it'll reflect back into the container. I can also create a new text file called hello world, and you'll see that it will be immediately available in the container. Okay, we've gone through a lot of flags, and it's starting to get a bit difficult to type, and it's also easy to make a mistake. So let's try Docker Compose. This is a more efficient way of running containers, and is usually used to start multiple related containers as different services at once. Just make sure you run the commands in the same directory as the Docker Compose file. When we go over the Docker Compose file, we can see that it's very similar to the Dockerfile. Here, we see the image being used, the name that will be assigned to the container, the command, work directory, publish ports, and volumes. What's new is version and services. Here, we specify the version of Docker Compose. If we don't specify the version, it will automatically use the latest version of Docker Compose, which might introduce breaking changes. With services, you can start multiple containers at once. You can name the service anything you want, but of course, it's best to give names that are logical. Once you have specified your Docker Compose file, starting it up is easy. To start, just type Docker Compose up to create and start the containers. If you want to stop the services, Docker Compose stop. Then Docker Compose start to start the containers again. Use restart if the containers are having issues, and then Docker Compose down will remove the containers. Now I'm going to remove the hello world text file which we created previously, and in the Docker file I'm also going to comment out the copy command, since I'm going to create a bind mount in the Docker Compose file anyway. The command also won't be needed, as I'll be using this in the Docker Compose file. So in the Docker Compose file, again, pretty similar to the Docker file, the only difference is we have version and services. Here we name the services Fast API. I'm also going to make some slight changes. Just like before, since we're using volumes, I need to point out in the command that the main.py file is inside the folder my code. Since I've made changes to the image, I'm going to rebuild it again. Now, instead of using docker run with all those flag commands, all we have to do is type docker compose up. This will create the container and start it for us. Oops, we have an error here. Remember, we can't have two containers of the same name. So what I need to do here is to delete my previous container and then run docker compose up again. Then we use docker process to see if the container is up and running. Then we can see that the container is running successfully. I can also run docker compose up in detached mode so that we still have control of our terminal. Now to stop the container, all I have to do is run docker compose stop. And because of the docker compose file, I don't need to specify which container to stop. Then to start the containers again, simply write docker compose start. And if the containers are stuck for whatever reason, we can run docker compose restart. You can see that the status of the container has been up for 5 seconds because it has just been restarted. Then to remove the container, simply run docker compose down. I hope that this video has helped you to be more comfortable with Docker. If you need more details on any of the concepts, please refer to the Docker documentation. Otherwise, if you need help with anything, we here at Melio are more than happy to help. Now, to end things off and to challenge your newfound Docker knowledge, I'm going to give you a little test in the form of a joke. Why do developers prefer Docker? Because it helps to contain their excitement.